Okay, I'm going to start chapter 8 here now. So chapter 8 is really just some applications of the integral. We saw that in chapter 6 in Calc 1. There's applications of the integral. So this is just some more applications to know. We're just going to do the first 3 sections also. So section 8.1 is arc length. It says that if f prime is continuous on the closed interval AB, then the length of the curve, y equals f of x, from A to B is given by this integral here. Okay, that's the general formula that you're going to use in every single problem in 8.1. Okay, so as an example, what if we have the function y equals 1/6 x cubed plus 1 over 2x, where x is going from 1/2 to 2. So I want to find the length of this curve from 1/2 to 2. Now, this is not a line, right? So it is a curve. This is the formula that I got to use, okay? I'm going to have to know y prime, because that's involved in the integrand. So y prime, bringing down the power, you got 3 over 6, that's 1/2 times x squared plus 1/2 times the derivative of 1 over x is x to the negative second. So 1 over x squared, so minus 1 over 2x squared, that'd be at the end of the derivative there. Okay, and using the formula, I'm going from A to B, so A is 1/2, B is 2, and 1/2, that's in common to these two terms here, so I'm going to go ahead and factor that out. So I got to the square root of 1 plus 1/2 times x squared plus 1 over x squared squared dx. Okay, so that's the integral that we need to find. 1 is the same as 4 over 4. 1/2 squared is the same as 1/4. Also, when I square out x squared minus 1 over x squared, I get x to the 4th minus 2 plus 1 over x to the 4th. Okay? So then the next thing that I'm doing here is let me factor out a 1/4 out of these two parts here. So I got 1/4 times 4 plus x to the 4th minus 2. 4 minus 2 is 2, plus 1 over x to the 4th. Okay? And the square root of 1/4, that's 1/2. 1/2 is a constant. I can bring that out of the integral. Times the square root of x to the 4th plus 2 plus 1 over x to the 4th. That's going to factor, and that looks very similar to what we just did up here, right? The only thing is I got a plus 2 instead of a minus 2. So it's going to be x squared plus 1 over x squared squared underneath the radical there. Okay? And taking the square root of something squared is just going to leave me with the term that I'm squaring there. So on the next line, I'm going to have 1/2 times the integral going from 1/2 to 2 of x squared plus 1 over x squared dx. Okay, and let's see, when I get the antiderivative here, I'm going to have 1/2 times 1/3 x cubed plus the antiderivative of x to the negative second power. That's going to be x to the negative first power divided by -1, or minus 1 over x. That's the same thing. And I'm going from 1/2 to 2. Okay. So now, when I plug in these bounds, plug in the upper bound first, we got 1/2 times 2 cubed is 8, so it'll be 8/3 minus 1/2, and then minus, when I plug in 1/2, 1/2 cubed is 1/8 times 3, 8 times 3 is 24, so 1 over 24, minus 1 divided by 1/2 is the same as 2. Okay, and when I simplify this guy here, I get 33 over 16. By the way, every single problem in section 8.1 and all of chapter 8, by the way, is always going to be positive numbers. Okay, so keep that in mind here, that I should never get a negative, which makes sense. You can't have a length of a curve be some negative number. That doesn't make any sense. So the length of this curve, going from 1/2 to 2, is a length of 33 over 16. Okay? If we try another example, suppose that I want to find the length of the curve y equals the ln of cosine of x, where x is going from 0 to pi over 4. Okay? Well, we need to get the derivative of that equation, because the derivative is me used in the formula here. And the derivative of the ln of a function is 1 over the function times the derivative of the function. So I got 1 over cosine of x times the derivative of cosine of x, that's negative sine x. So I get negative tangent x for y prime, or dy dx, same thing. Okay, so using the formula there, this guy up here, let's see, I'm integrating going from 0 to pi over 4, the square root of 1 plus negative tangent x squared, that's tangent x squared, okay? 1 plus tangent squared x, that's the same as secant squared x, okay? And the square root of secant squared x, that would be actually the absolute value of secant x. But I don't need absolute value bars because of the integral the bounds that I'm integrating on. Okay, so I'm going from 0 to pi over 4. Well, here's a graph of the secant curve. If I go from 0 to pi over 4, the y values of secant x are going to be positive numbers anyway. So I don't need the absolute value bars there. Okay? Now if I were going from like pi to 5 pi over 4, I would need it'd be the opposite of secant x dx. Okay? I'm not going from, pi to pi or pi to 5 pi over 4, okay? But that's what I would do in that situation. So I just lose the absolute value bars there. And let's see, if I'm integrating secant x, that is the ln of the absolute value of secant x plus tangent x. We saw that integral, let's see, I'm getting a note here. So it's, it was in section 7.3 here. So that involved the sneaky little trick. I need to multiply the top and bottom by secant x plus tangent x. And I'm setting myself up for a u substitution. Okay, so I get the ln of the absolute value of secant x plus tangent x. I'm integrating this on the interval of 0 to pi over 4, so plug in the bounds now. When I plug in pi over 4, secant of pi over 4, let's see, cosine of pi over 4 is adjacent over hypotenuse. So the adjacent side is 1, the hypotenuse is root 2. Secant of pi over 4 would be the reciprocal of that. Okay, so instead of 1 over root 2, I'm going to have root 2 over 1 plus tangent of pi over 4 is 1 over 1. That's 1. Okay. And I can lose the absolute value bars because root 2 plus 1 is already a positive number there. When I plug in 0 here, secant of 0 is 1 because cosine of 0 is 1. And tangent of 0 is 0. Okay, so I'll be subtracting the ln of 1. The ln of 1 is 0. And so my answer is going to be the ln of root 2 plus 1. Again, keep the answers in exact form here. There's no reason at all to use a calculator for any of this stuff here. Okay, we are looking for exact answers. Okay, so that'd be the length of this curve going from 0 to pi over 4. Okay. Just to show you another example, so suppose I have a line going from x1, y1 to x2, y2. Okay, so you have y equals mx plus b. And if I want to know the length of the curve from this first point to the second point, well, that's the same as the distance of the curve, the distance of this line from the first point to the second point, and I can use the distance formula that I'd see in an algebra class to get that. Okay, here's the distance formula. So we're basically showing that, you know, the length of the curve when you have a line is going to result in the distance formula, the distance between 2 points. So, well, f prime of x, that's going to be the slope of this line. Okay, so the slope of a line, change in y over change in x, so that's y2 minus y1 divided by x2 minus x1. Okay, and the length of this curve, so now keep in mind that, you know, when I'm using this formula, everything about this integral is in terms of x, okay? So the conditions on x are, I'm going from x1 to x2 for the bounds. And I'm integrating the square root of 1 plus f prime of x is the slope of this line, so y2 minus y1 divided by x2 minus x1 squared dx. Okay? So then the next thing here, now this whole integrand is a constant. Okay? Just like 5 is a constant. So, you know, because I'm integrating in terms of x. Well, again, everything about this is a constant. So I'm going to take the constant times x for the antiderivative there, and plug in my bounds, plug in the upper bound first, lower bound second, so I get x2 minus x1. And the square root of x2 minus x1 squared, that's x2 minus x1 in the denominator of this. So I'll be able to cancel out those x2 minus x1 terms there. And that leaves me with the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, well that formula there, that's the same thing as the distance formula that you see in the algebra class. Okay, so this is one way to show, you know, where the distance formula is coming from. You know, so okay. Again, this is, you know, all the problems in this section are going to be, you know, just reusing this integral formula over and over again. So, but that's kind of all I had here with section 8.1. So you should be able to look at these problems here for homework. And we'll go ahead and stop the video right there, and I'll get into 8.2 in the next one.